Start.
Hello there. We are students from SirMVIT Bangalore, and this video features the analog design contest organized by Texas Instrument India. In this video, we are going to show the problem statement which is given under phase 1A by Texas Instrument. And the problem statement says that we have been given with a non-inverting differentiator circuit, and we have to show that the transfer function of this circuit or the differentiator is given by this. So we will derive this transfer function. For that, you can see we have the non-inverting differentiator here. We have got two resistors R1 and R1 of equal values, and the two input or the base resistors R2 equal values. Right. So here we are using a capacitor whose one end is grounded, the other one is directly connected to the inverting terminal of the op-amp, and the op-amp used is TL082. Fine. So here the transfer function is given by this, the expression which we already showed you. Here A is the open loop gain of the op-amp, and it is equal to GB by S, where GB is the gain bandwidth product. So let's see. So if A is the open loop gain or the differential gain of the op-amp, then A must be equal to, or A should be equal to the ratio of the output voltage and the difference in the input voltages at the two terminals, the input terminals. That's why A is equal to V0 by VB minus VA, or A into VB minus VA is equal to V0, where VA and VB are the potentials at point A and at point B. Also, please note that the potential at point C and point A are same because they are the same point. So, in the next step, we have VB minus VA equal to V0 by A. As you can see, we get the expression for VA as VB minus V0 by A. Fine. Differentiating this equation, we get dVA by dt is equal to dVB by dt minus 1 by A dV0 by dt. Now, applying KCL at point C. Here, as you can see, we have different currents which come to this junction and leave the junction. You can see I1 and I2, they are coming to this junction, and I3 is leaving. So, applying KCL, we get I1 plus I2 equal to I3. I1 plus I2 equal to I3. Also, I3 is the current through this capacitor, and as we know, the current through the capacitor is given by C, the capacitor value, multiplied by the potential, the differential of the potential difference across it. So I3 is equal to C dVC by dt. Also, that we have here, C dVC by dt, and the current I1 is equal to VI minus VA divided by R2, and I2 current is equal to V0 minus VC divided by R1. Now VC is same as VA, so we have just replaced VC by VA here, and we get VI minus VA by R2 plus V0 minus VA by R1 is equal to C dVC by dt, or in turn which is equal to C dVA by dt. Now this value dVA by dt, we are going to substitute its value from here, from this equation, and we get VI minus VA by R2 plus V0 minus VA by R1 is equal to C into dVB by dt minus 1 by A dV0 by dt. Fine. Now, please note the potential at point B is given by VI into R1 divided by R1 plus R2. For this, as you can see, the input voltage is VI, and here this R1 and R2 resistor network, they form a potential divider. That's why the potential drop across this resistor R1 is the potential which is given to this non-inverting input terminal. That's why our VB is equal to VI R1 by R1 plus R2, and from a previous equation here, we have VA equal to VB minus V0 by VA, so that becomes VI R1 by R1 plus R2 minus V0 by A. Now, we substitute this in this equation, and we get an equation like this. So here on the left hand side we have just substituted, no, we have not substituted anything on the left hand side, we have just rearranged it. On the right hand side we have substituted for Vb. So as you can see, d by dt of Vi R1 by R1 plus R2. This is what we have substituted, just everything is same. Coming here, the next step, we substitute for Va as Vi R1 by R1 plus R2 minus V0 by A. On the left hand side, right hand side remains the same. We have just differentiated R1 and all these. This whole thing is a constant. Vi is changing, so it's dVi by dt. So rearranging this equation, the whole equation, we get this V0 by R1 plus V0 by A into R1 plus R2 by R1 R2 is equal to C multiplied by R1 by R2 plus R2 d by dt of Vi minus 1 by A d by dt of V0. Now taking Laplace transform of this particular equation, we get this below equation. So here we have taken Laplace transform, so it's a function of S everywhere. So V0 of S by R1 plus V0 of S by A into R1 plus R2 by R1 R2 is equal to C S R1 by R1 plus R2 into Vi of S minus S by A into V0 of S. So rearranging, getting all the V0 of S terms on one side and Vi of S terms on the other side, we get this equation as you can see. And it's quite clear from this equation that the transfer function, before getting the transfer function, we have multiplied by resistor R1 throughout the equation. So we get this particular equation. And from here, we have just taken the ratio V0 of S by Vi of S as this. Now, as it's given that the open loop gain A is the GB by S, where GB is the gain bandwidth product, we are going to substitute A as GB by S and let's see what we get. So for this, we will write it as R2. So A is equal to GB by S, so we can write it as S by GB into 1 plus SCR1 plus R1 by R2. Now, if you see this denominator, here we have an S square term. This gets multiplied with this particular term SCR1 and it becomes S square. So the denominator is a second order expression, or you can say second order equation in the denominator that we are getting. Now this particular denominator of second order represents an equation for an underdamped start. So the next step is to simulate the given circuit. So for the simulation we have used TINA simulation software provided by TI, and we have the circuit here. We have built the circuit as you can see. We have the resistor R1 2.2k, R2 1k, and we have the capacitor 1 microfarad, and this is the op-amp used TL082. So after simulating, while simulating, we have given the input as sine wave 100 Hz 20 millivolts peak to peak. So after simulating we get the Bode plots as shown here. Now this one is the frequency response and the below one is the phase response. So the frequency and the phase response, they match as given by the problem statement as you can see here. So this is the frequency response and here is the phase response, and it exactly identical to what we get on the simulation screen. Now here, for determining the gain bandwidth product, we have already taken it. As you can see, we have calibrated it to the 3 dB down frequency, and we are getting the gains as 62.88 3 dB down, and the frequencies are 15.13k and 16.47k. So that gives a bandwidth of around 1.34 kilohertz. So that is the bandwidth what we are getting in this plot.